Thanks, Scott. So I'm going to talk about FireSim and as well as FirePerf, which is a set of tools inside FireSim. So FireSim is basically a platform that we've been building at Berkeley to let you simulate, debug, and profile RTL designs running on cloud FPGAs. And of course, this is work done with a bunch of collaborators at Berkeley. All right, so just some quick background that we all sort of know, but what does the architect or chip developer's design flow usually look like? Well, usually we start with high-level simulation to sort of spec out an idea. Then we write RTL and some software. We plug this into some ecosystem that gives us a bunch of nice components. Then we move to our sort of first co-design stage where we are simulating this in an RTL simulator, something like Baremetal. We run Microbenchmarks on top of this to evaluate our design and see how it behaves both functionally and maybe in terms of performance too. Then we'd like to move to some sort of faster simulation environment, right? This is where we want to actually boot maybe an operating system on our design and run our full software stack that we would run once we get a real chip. And we want to get real performance measurements so that we can make sure our design behaves like we want once we get a real chip back. Of course, then we go through the tape out process, we get a chip, and we sort of have our real design. But at this point, obviously, we can't really make any hardware changes. So we saw an opportunity in sort of this number 4 space here to build a set of tools that would let us do fast simulation using FPGAs. And that's really where FireSim fits into this flow. So you might ask the question, what about FPGA prototyping? So that's a commonly used tool for trying out a system that you've built. But the reason that we don't want to use FPGA prototyping is sort of modeled on this slide. So we can consider something like a taped out SoC. So we're writing some RTL. Once we tape it out, it's going to run at a gigahertz, and it's going to talk to some DRAM. Let's say that DRAM has 100 nanoseconds latency for the sake of example. Well, software running on your SoC is going to see 100 cycles of DRAM latency. But if we build an FPGA prototype of the system, obviously our RTL usually isn't going to run at that full 1 gigahertz, right? We're going to get something like 100 megahertz. But of course, this FPGA is still going to be talking to real DRAM with that same sort of latency. And so if you're doing performance measurements on a design running like this, you're going to get incorrect results. So in this case, the SoC is going to see just 10 cycles of DRAM latency. So this sort of brings us to the general difficulties with FPGA prototypes, right? This is because every FPGA clock is 1 cycle of the simulated machine's clock too. You're also exposing FPGA resources to the simulated world. So for example, when you connect that real DRAM to the RTL running on the FPGA, you're just exposing the real world latency of that DRAM. This has 3 implications. First off, the things that you're trying to model, the IOs that you're modeling, won't be accurate because the FPGA resources aren't necessarily an accurate model. If you compare sort of the ratios of how fast your RTL is running on the FPGA versus those real world resources. Your simulations are going to become non-deterministic usually because you are exposing them to the outside world. And when you port across different FPGA host platforms, you're going to get different simulation results, just sort of by number 2 here. So in building FireSim, what we wanted is hardware simulators that do the following. So we want to be as close to silicon speeds as possible. So this is why we're not just using software RTL simulators. We want to be as detailed as silicon. So we really want to truly model the RTL we have. We want to have many of the benefits of software-based simulators. So if you use something like Verilator, where you can just stick prints in your Verilog, you can have asserts. We want those sorts of features in an FPGA simulator, which traditionally you don't get with FPGA prototypes. And we want them to be low cost. So our thesis here is that FPGAs are the only viable basis technology for doing this. And so we build FPGA accelerated simulators with software-like flexibility through this open source tool. So how are we going to do this? Well, we're going to take advantage of a bunch of useful trends that have come about in the past couple of years throughout the architect stack. So the first one of these is just going to be the presence of FPGAs in the cloud. So it used to be the case that if you wanted to build one of these FPGA accelerated simulators, you had to go buy expensive FPGAs, set up your own cluster, manage that cluster, and then reproducibility was a nightmare because you had to go tell other people how to build your exact cluster. So FPGAs in the cloud, for example, EC2F1, which we're going to use, basically makes this process simpler. Everyone has access to the same common FPGA infrastructure, and we can do things like share bit streams really easily. Then we need something to simulate, and of course that's written in RTL, but we want to automatically take RTL and convert it to an FPGA simulator, and that's where we want an RTL where we can do transformations on something like an IR that sits behind that RTL, to build our simulators automatically. Again, we need something to simulate. So there's this big blowing up space of silicon-proven SoC implementations. And in particular, if we want to do something like architecture research, adding things like accelerators to SoCs, then we want to actually be able to run software on our systems. So the systems that we're simulating need to implement an ISA with broad software compatibility, and RISC-V is really getting there. These days, there's a huge explosion in the software ecosystem, and you can pretty easily get most software that you would want to run up and running on RISC-V. So at a very high level, what does FireSim do? So FireSim is going to let us build fast, automatic, and deterministic FPGA accelerated hardware simulators that you can use both for pre-silicon verification and performance validation. So what we're going to take as input is an RTL design. Usually that's in Fertile via Chisel, or also now you can do things like pull in Verilog designs through the Yosis Verilog to Fertile flow. We also have other ways of handling Verilog, which I'll talk about later in the talk. We also ingest I/O models, and I'll talk specifically about what those are in a second, but these are what accurately model timing of things like DRAM. We also pull in things like workload description. So FireSim has a tool built in that'll let you automatically build Linux distributions for things like RISC-V SoCs. So again, we're going to produce these fast cycle exact simulations of the design with all your models plugged in. And we have tons of automation to deploy this on top of cloud FPGAs. So the three distinguishing features in FireSim, we're not building FPGA prototypes, we're building simulators. So we're going to take those designs that you want to simulate and automatically transform them into FPGA accelerated simulators. And by doing so, we get the ability to tack on debugging capabilities, resource optimization capabilities, and profiling capabilities. And I'll talk about each of these different things in detail a bit later in the talk. We're going to use cloud FPGAs. That makes it very easy to scale our simulations. So we can start with just working on a design, iterating on it with one FPGA. And when it comes time to run large benchmarks, for example, spec, we can automatically spin up to, say, tens or hundreds of FPGAs in parallel. This also makes it really easy to collaborate with other researchers. And it's going to be open source, and you can go to that link to read more about open source FireSim. Okay, so how are we going to do this? So the first distinction we need to make before we build this kind of simulator is to separate out the notion of target and host. So this is true of software RTL simulators too, where the target is going to be the machine that we're trying to simulate, and the host is going to be the machine executing the simulation. So in our previous example, it's going to be that RTL for that SoC, as well as the DRAM that would be attached to it too. Well, ideally, we want to close simulation world around this so that we get determinism. Then the host machine can look like this. It can be just an FPGA fabric attached to DRAM, or it could be a multiprocessor commodity server blade type thing that'll run a software RTL simulator. So FireSim is going to generate FPGA-hosted simulators. So the analogy here is just like Verilator would generate a multiprocessor hosted simulator, FireSim is going to generate an FPGA-hosted simulator. So the way we transform a design in FireSim, so we have an example design like this on the left, same one we've been using all along. What we're going to do is we're going to take the RTL and we're going to transform it into a latency insensitive model using a Fertile transform. So we're essentially going through the design in Fertile at sort of the highest conceptual level. You can think of it as clock gating the whole design so you can control how cycles pass on the FPGA. Then we're going to tack on FPGA-hosted models for different I/O components. So for example, a model for DRAM that presents accurate timing to the RTL design. Then we're going to connect all of those components together using token channels to maintain synchronization and timing accuracy. So once we do that, we want to allocate host resources to models. So I mentioned that DRAM model is an FPGA-hosted DRAM model. So it's basically going to sit in the FPGA fabric and present, in our example, 100 cycles of latency to the simulated system. And it's going to have capacity backed by the physical DRAM that's attached to the FPGA. And then, of course, we need to drop down our design too. So this is sort of what a FireSim-hosted simulation looks like on an FPGA. So there are models sitting on the FPGA fabric around your actual RTL design. And so once you do this, your SoC will see realistic DRAM latency. And the same thing translates to other sorts of IOs. Okay, so what are the benefits of doing this? So your simulations now are going to be deterministic because your simulated system is isolated from the world around it. you're going to get identical results on different hosts. So if you run this on an FPGA, or you run a simulation of the simulation on a CPU, you'll get the same results. And this gives you support for software co-simulation, and we'll talk about a bunch of examples of this. It'll let you simulate large targets over many hosts. So because we have this token-based synchronization mechanism, we can split things even across FPGAs, across hosts on EC2, and build up large-scale simulations. And we can add debugging and instrumentation tools that basically let us pull out lots of data from the simulated system without perturbing that system. And I'll talk about that towards the end. And the last thing this enables is resource optimization. So we can change our compiler so that we can fit more stuff on the FPGA by basically trading off simulation performance for resource utilization on the FPGA. Okay, so what can you actually do with FireSim more concretely? So here are a couple of examples of target designs that you get in FireSim. So one is ChipYard. So this is a fairly recently released framework from Berkeley that basically has a large collection of open source IP that makes it easy to construct complex RISC-V SoCs. So about last year at this time, we sort of realized that, okay, at Berkeley, we're shipping out tons of RTL for various components, but there's no real one-stop place to put all of these pieces together. And that's basically what ChipYard has become. So you get things like in-order and out-of-order cores, caches, interconnects, a variety of accelerators, and a variety of peripherals too. There are also designs that other people have added. So the NVIDIA NVDLA GitHub organization has a fork of FireSim that supports simulating the NVDLA. People have also done work to integrate Vivado HLS generated accelerators, so you can rapidly prototype accelerators plugged into Rocketship. We have some early work pulling in PicoRV32 through Yosis, through Fertile, into FireSim. And of course, you can always bring your own design, whether it's Chisel or Verilog in some cases. So what are some example use cases? So there's the sort of obvious use case of just measuring performance. So we've done this in some papers, for example, evaluating the performance of our DRAM model. We could very easily spin up 10 cloud FPGAs to run all of spec in 2017 with full reference inputs on Rocketship in less than a day. People have done all sorts of design space exploration for different sorts of systems. A nice thing that we can do is because we're building from generators, we can create sort of a parameterization space of your design, and we can quickly, in FireSim, ship out lots of parallel FPGA builds to get bit streams for a variety of designs, and then also automatically run all those examples in parallel on lots of FPGAs. So you can very rapidly do a design space exploration running significant software stacks on top. Other people have used this for evaluating security. Timing-based attacks in speculative processors, enclave evaluation, accelerator evaluation of various kinds. Another use case is debugging and profiling your design. So, of course, what happens if we run billions of cycles into simulation, but then it just hangs on the FPGA? So there's been work for debugging chisel designs at FPGA speeds. That's adding things like assertions and printfs. And I'll talk about all of these things in more detail a little bit later on. Profiling RISC-V SoCs, so doing hardware-software co-design when there's a big complicated system and you want to understand what's happening inside of it. As well as golden model comparisons between the FPGA and a software golden model of your system. The use case I'm going to talk about in detail, though, since it sort of covers many of these components, sort of the original reason we built FireSim, which was to model data center scale systems. This is what was covered in our original ISCA paper about FireSim. So why do we want to do this? Well, the data center hardware environment, as we all know, is changing pretty rapidly. There's lots of custom silicon in the cloud now, new proposals for faster and faster network technologies, new memory and storage hierarchy components, as well as new data center architectures. So in particular, disaggregated data centers are being proposed more commonly these days, where you take components that commonly used to just live on a single server blade, and you split them out across a high-performance interconnect inside the data center. So how do we map a data center simulation onto a platform like EC2F1? So what I'm showing you on the right-hand side is an EC2F1 instance. This is an F1 16x large instance. And basically what this consists of is a beefy Xeon or two attached to 8 Xilinx UltraScale FPGAs. over PCIe. So this is sort of the fundamental host unit that we'll use in this example that we're building. So of course, if we want to model a data center, we need to model all of that hardware at scale, cycle accurately, and we want to run real software on top. So the way we're going to do this is by mixing software models and RTL models running on the FPGA. So this is an example of that sort of co-simulation. So we're going to take the server simulations. These are a good fit for the FPGA because we have tape-out proven RTL, things like Rocket and Boom. We can build SoCs out of them, transform them into an FPGA simulator, and run those on the FPGA. We can run network simulations, on the other hand, on the host CPUs here. So these are C++ switch models that still speak in the same token interface to coordinate simulations, but they're just software. So we can have these link models that talk between switches and servers and switches and other switches cross a variety of transports. So we can have a switch model that communicates across all of these FPGAs on a single 16x large instance, and then later we'll see scaling across many instances too. Okay, so we're going to build this sort of from the ground up. So we're going to start from what we're calling a single server SoC's RTL design. So here the example we're going to use is a quad-core rocket chip-based system. We're modeling it as if it's running at 3.2 gigahertz. So of course, it's not going to run at 3.2 gigahertz on the FPGA, but the world around it is going to be constructed such that it looks like it's running at 3.2 gigahertz. We're going to give it, let's say, standard memory hierarchy components. And in particular, a new thing that we added when we did this work was 200 gig Ethernet NIC design written in Chisel. And so if you just drop this on an FPGA, this will take about a quarter of one of these FPGAs on EC2F1. Of course, this isn't the full model, right? This is just RTL design. So what we're going to do as our first step is transform this into an FPGA simulation of one server blade. So now what I showed you on the previous slide has sort of been zoomed out a little bit, and that chunk of RTL has now been transformed into this FPGA simulator, and then we tack on a bunch of models sitting around it. So I showed you that DRAM model a bit earlier, that's sitting on the FPGA fabric. We have a network model, the NIC SIM endpoint that's shown in this diagram, and models for a variety of peripherals too. So if you look at the specs of the system, basically what we've tacked on here is 16 gigs of DDR3. So the capacity is provided by the DRAM attached to the FPGA, and the timing of DDR3 is provided by the DRAM model sitting on the FPGA. So the nice thing here is this will take up about a quarter of one of these FPGAs, and we're only using 1/4 of the memory channels to model this sort of system. So if you run this without a network simulation, this will run at about 150 megahertz on these FPGAs. And when we run it with a network simulation talking to a switch model, this will run at 40 megahertz. And I'll explain exactly why that's happening in a couple of slides. So then what we want to do, we're trying to simulate a data center, so we want to scale out. So as I mentioned, you can pack 4 of those simulators I just showed you on one FPGA on EC2F1. So there are also single FPGA systems on EC2F1. So the cost shown here is for one of those. You can model this total of 16 core, 64 gigs of DDR3, talking to a network model, this 4-node network system for about 50 cents per hour on EC2. Then we want to keep scaling out. So we're going to switch to that F1 16x large instance, host instance that I showed you earlier in the talk. So we're going to stamp out 7 more copies of that 4-node simulation. And here you can see that top of rack switch model, just a C++ model running on the host CPU. So that switch model is talking to every single one of these FPGA simulations over PCIe to keep them in sync and move data across. So at this point, we can use this to model 32 of those original server blades I showed you with all these aggregate statistics. So the network we're modeling here is a 200 gig Ethernet network where each link is 2 microseconds. So we can run this on 8 FPGAs, which is one of those F1 16x larges, still fairly cheaply, $2.60 per hour on the spot market, which is pretty cheap given how much these FPGAs cost. And you can run this at about 10 megahertz. Okay, so that's modeling a single rack in the data center. So of course we want to keep scaling out. But first I'll quickly talk about the network model. So how these network models actually work. So the real sort of implementation detail behind these is this link model. So you can see this link model communicating, letting you communicate between a port on one of those switch models and the top level, the NIC interface that's in one of these FPGA simulators. So to maintain global cycle accuracy here, we basically need to ship a token in each direction for each link for each cycle. And so when we need to model a particular latency, this link model is going to maintain some number of tokens in flight. So if we want to model 2 microsecond links and our endpoints are running at 3.2 gigahertz, we're going to have 6,400 tokens in flight at any given time. And to model a particular bandwidth, we're just going to size the width of those tokens to match whatever rate we want. So 200 gigabits per second at 3.2 gigahertz will give you approximately 64-bit wide tokens being exchanged per cycle. So this link model is target transport agnostic, so it's just shipping around bits. It's the switch and the endpoint's job to actually understand what those bits mean. So we provide Ethernet switch models, but you can change out that fairly easily. These are also host transport agnostic, so you can write your own backend to have these link models cross a variety of host transport. So we provide shared memory, socket-based transport, and a PCIe-based transport. And that's basically what we need to construct these large simulators across a large number of instances. And you can also downgrade this to a no performance impact functional network model. So I alluded to the fact earlier that when you use these network simulations, you lose performance, and that is because of the fact that you need to exchange tokens every cycle. The nice thing is, if you have some latency to model, you can batch that token exchange to get some more performance. Okay, so back to this 32 node rack example. We want to scale out further from here. So we're going to spin up some more F1 16x large instances on EC2. In this case, we want to model 256 simulated nodes. We're going to add 7 more F1 16x large instances. And we're going to add another M4 16x large instance, which is just a regular compute instance that's going to run another C++ switch model that's going to be an aggregation switch that talks to each of those top of rack switches. So in our simulated system, we've essentially added another layer in the switching hierarchy. So you can think of it so far as an aggregation switch, 8 top of rack switches, and each of those 8 top of rack switches is talking to 32 FPGA simulations. So still across these 8 F1 16x large instances, we're still globally coordinated running these cycle accurate simulations. Okay, so we want to hit a magic number of 1,024 nodes, so we can do this one more time. So now we have 4 aggregation switches talking to 1 root level switch that's just, again, modeled on a regular EC2 instance. So we're getting global cycle accuracy across these 1,024 server models. And that's how we scale out in this example. So here, the link models between the switch models are an example of a link model that crosses over sockets. So that's the backend implementation that's letting these communicate between different EC2 instances. So here, to model this system, we're using 256 FPGAs, and this thing will run at about 6.6 megahertz. So the sort of punchline here is that because we're using cloud FPGAs, we can take advantage of these FPGAs that would cost millions of dollars to buy to simulate these 1,000 nodes cycle exactly with this synchronized network simulation tying them all together. But to us, it only costs hundreds of dollars an hour to run this scale of simulation. Obviously, most users aren't going to be running this scale of simulation. This is just an example to show you what this sort of system is capable of. Of course, we want to run software on this sort of system. So we can run a very simple benchmark on top. We can say all 1,024 of these nodes boot Linux. And then we can do something simple like saying 512 of them are going to run memcached, 512 of them are going to run a load generator, and we're going to apply the load to these memcached servers. So these are measurements from a 1,000 node FireSim simulation where we get some baseline number for just crossing a single top of rack switch. And then we can force all of these transactions to happen across an aggregation switch. And sort of as you would expect as validation, our latency goes up by about 8 microseconds. So that's a very simple example. We wanted to do a little bit more validation. So another example that we tried out was to reproduce tail latency effects from actual real x86 clusters. So there's a paper on Eurosys 2014 that basically showed the effects of thread imbalance in memcached. So what I mean by thread imbalance is essentially we have a system like you see here, 4 physical threads, and we configure memcached to have 4 software threads. This is the no thread imbalance case. But you could imagine someone misconfiguring memcached and saying, okay, more software threads is always better. Well, let's make it 5. Well, what this paper actually identified, among many other things, is that if you have this sort of thread imbalance, your median latency latency will be unchanged. So if you were just looking at sort of middle of the road effects, you wouldn't notice this misconfiguration. But if you look at your tail, this thread imbalance case causes a huge blow up in your tail latency. Okay, so let's run a similar experiment on an 8-node cluster in FireSim. So we're going to take a single node, we're going to run memcached on top. We're going to take 7 other nodes, network together over Ethernet, and run the mutilate load generator on top. So that's the same load generator that was run in that paper, except now we're on a RISC-V system, our own NIC, all sorts of stuff. So here we can look at this result. So again, on the x-axis, we're looking at queries per second. So we're increasing load on the system. And then we're looking at request latency. So I'll show you the median and I'll show you the 95th percentile. So the 4 threads case here means there's no thread imbalance because we have 4 physical threads in the system. The 5 threads case will induce thread imbalance. It's basically the scheduler not knowing what to do with that extra thread, and it kind of moves around over time. So in the median case, you see overlapping lines here, and you see basically no difference between the thread imbalance and no thread imbalance case. Now, if we add the 95th percentile, so you'll see these black diamonds. These are the 4 threads 95th percentile case. So what we expect is not huge blow up at the tail, and that is in fact what we see. So there's some ping-ponging around here, and I'll show you another set of lines in a second that explain what's going on here. But there's this ping-ponging, but then it sort of flattens out at the tail here. So our 4 threads case is a little blow up, but nothing crazy. But if we look at the gray triangles, so all we've changed, we're still applying the same exact load. We just misconfigured memcached to have an extra thread, and we see the same blow up in the tail here at the 95th percentile. So we were actually interested to see what was going on here. And what is actually happening is even in the 4 threads case, the scheduler gets a little confused when there's sort of medium load and it starts to misplace threads, which is why you see those black diamonds starting to jump up here. But under high load, it figures it out and does the right thing. And to sort of test out this hypothesis, we just pinned threads, and these are these gray pluses that you see. And we see sort of a flat line in our tail latency. So these are effects that they observed on real x86 systems. And so as validation of being able to observe these sorts of effects on our RISC-V systems, we ran these sort of benchmarks, and that's what we could see. Okay, so now I'm going to talk a little bit about the actual internals of FireSim. So the first thing I'm going to talk about is mapping the cloud FPGA. Since we just talked about all of the scaling to hundreds of FPGAs, how do we actually do this without introducing ridiculous complexity? So the way FireSim exposes you to these instances is sort of very controlled. So as a user, you have this manager instance. You just think of it as a regular remote machine that you SSH onto. You write your RTL there. You run your verilator simulations there, all of that good stuff. But then when you actually want to ship out builds, we have this ability to spin up a build farm. And we have this ability to spin up a run farm when you actually want to run simulations. And these are sort of hidden from you as the user who is just interacting with this manager instance, which is basically the head node on EC2. So the way we run simulator builds, for example, is you run just one command, FireSim build AFI. What this basically does is it looks at a configuration file where you've spec'd out all of the configurations of your design that you want to build, and then the rest of the process is automated for you. So it'll automatically spin up this build farm with the right number of instances. It'll ship out all of your source code. It'll run Vivado on the thing. It'll copy back your QR results to make sure you've met timing and that sort of stuff. And it'll generate a bit stream. And then at the end, it'll tear down your instances automatically. So this is one of the features that lets you do big design space explorations really easily. So you can have 100 configurations that you want to build. And this is an embarrassingly parallel workload. So we just ship it out to 100 instances and do it quickly. So we can do the same thing for running simulations. So here we have a little bit more granular control. So you can essentially in a configuration file spec out how many instances you want of various kinds. Then you can run FireSim launch run farm, which will spin up these instances in the background. You can run FireSim infra setup, which will ship out all of the components of the system you're trying to model. So for example, if we're modeling this 4 SoC system connected together with an Ethernet network, we'll define this topology in Python in the manager. And it has this mechanism to automatically compile that down essentially to some set of EC2 instances, and then it knows how to ship around all the infrastructure in the background. So we can do that. Then we can run FireSim run workload. So this is basically the sort of job monitoring, run your job step. So you can define a workload that you want to run on each of those nodes in the simulation. So for example, memcached, booting on Linux, all of that sort of stuff. And you can also define what results you want copied back at the end, collateral from inside the simulated system, outside the simulated system, and those sorts of things. The simulation will run, automatically shut down, tear down instances if you'd like, or you can also manually run FireSim terminate run farm to kill those instances running in the background once your simulation is completed. So we tried to automate this whole process sort of out of necessity, because we couldn't run these 1024 node simulations on hundreds of FPGAs if we had to do it all by hand. But this translates very nicely to even a user just running a bunch of spec workloads on a single node system. Okay, so let's dive a little bit deeper into the compiler in FireSim. I gave you sort of a high-level idea of how this works, but we'll try to answer another question, which is, what if the design we're trying to model doesn't fit on one FPGA? So Golden Gate is the new compiler inside of FireSim. So if you're familiar with FireSim, it used to have a compiler inside called Midas. This is the next generation of that compiler. So your models here are basically structured as a data flow network. And dividing up your models this way lets you have optimizations that apply to these things. So an example of one of these optimizations is to optimize highly ported register files into something that runs nicely on FPGAs, or that maps nicely onto FPGAs. So Boom in particular has these sorts of highly ported register files. And so what we can do is apply a resource optimization step here, which basically extracts these sorts of FPGA hostile memories. It'll generate utilization optimized RAM models. So the simplest case is if you have a bunch of ports, you can basically trade off host cycles, so reduce your simulation rate to basically pretend to expose multiple ports, even if your thing that you're actually mapping onto only has a single port. So this was applied to a Boom model, where previously on one of these FPGAs on EC2F1, we could only fit 4 Boom cores on one of these FPGAs. Once you apply this sort of resource optimization, we could now fit 6 of them. So we went from 4 Boom cores filling up the FPGA to 6 Boom cores filling up the FPGA, again, on the same exact FPGA. There's some more detailed results that I won't go into for the sake of time. Okay, the next thing I'm going to talk about is debugging in FireSim. So what happens when we run a simulation for a couple of hours and then it just hangs, right? We can't go back and run this in software simulation because it will take a really long time to get there, right? It might take weeks or months to get to the same place that FireSim got to after a couple of hours. So we need tools in our FPGA simulators to debug them. Okay, so the simplest version of one of these tools that essentially just gets us parity with FPGA prototypes is called AutoILA. This is essentially just giving us the same ability we have in Verilog to tag some signals and have them wired up to an ILA, except this is at the chisel level. So we can annotate certain interesting signals in chisel, and this gets automatically wired up to an ILA. So this is what was one of our early tools that we used to find some bugs in Boom. But that's not really what I'm going to focus on in this talk. That's just giving you ILA support in FireSim. I think there are a couple of more interesting features. The first is assertion synthesis. So of course, if you're running in software RTL simulation and you have asserts in your RTL design, those asserts will fire and tell you that some property was violated in your design. Normally, when you map down to FPGA prototypes, you lose these asserts. They don't mean anything on an FPGA, since there's not really a way by default to signal that information out. So in FireSim, what we can do is synthesize asserts. So we tack on some extra hardware on them, and we can tell when an assert fires in part of a design. Similarly, printfs have the sort of same property. If you have printfs in your RTL, they'll show up in a software RTL simulation, but when you map to an FPGA prototype, you lose them. So we can add the same sort of infrastructure around printfs because we're transforming designs, and we can walk the design in software. So we can put printfs in our RTL and have them show up on the host system when we're running FPGA simulations. So an example that we had in Boom is that we had some issues with the ROB having a valid entry being overwritten. Luckily, there was an assert here once we added assertion synthesis in FireSim, we could see this assert fire. So this is an example of the UART output you would get while booting Linux inside FireSim. So you can see at the top here, everything looks fine. We're getting pretty far. And if you were running without assertion synthesis, you would just basically get a hang here, right? And then you wouldn't know what's wrong. Even to get to this point in software RTL simulation, this would take you about 62 hours. In FireSim, we can do this in a couple of minutes. And so we can run to this point, see that an assertion fired. Through our transformation mechanism, we know which assert it was in the original source code, and we can report that to the user. And so now they have some information at least to figure out where to go and debug this problem. So a newer tool to enable debugging in FireSim, this is actually just a PR that's staged right now, is called Fromajo. So this is basically letting you do co-simulation for golden ISA model comparison in FireSim. So what we're talking about here is basically checking for divergence between some fast software ISA simulator that we're going to treat as the golden model and some RISC-V RTL implementation that we're trying to verify. So again, we want to be able to catch bugs deep into simulation. So what we're going to do is take the commit trace coming out of Boom and compare it with that functional simulator. We're going to use Fromajo as the golden model simulator. So this was a simulator developed by Esperanto that is actually designed for this purpose. And so what happens here is that when we get a divergence in a FireSim simulation co-simulated with Fromajo, we can basically dump things like registered state, simulator state, and exception and interrupt info. So we use this pretty recently to find this divergence that happens about 2 billion cycles into a simulation, where if you have an interrupt during a misspeculation, you have some messed up architectural state. And so we were able to identify this mismatch through this sort of debugging. So the way this basically works is that there's a bridge in FireSim. So bridge is another name, is a newer name for what we used to call endpoints. It's basically those models sitting on the FPGA. In this case, it's going to connect to the trace port on the simulated SoC. This is basically a drop-in replacement for Tracer 5, which is a feature I'll talk about a little bit later. This can be tested. This has currently been tested with Boom in the example I showed you previously, but you can connect this basically to any RISC-V core that has that trace interface. And you can also tack on some modifications to FireSim workloads to sort of ship around all the infrastructure that you need to enable this sort of simulation. So things like the device tree entries and the ROM code. Okay, so another piece of FireSim internals is a project called FirePerf, which is basically going to let us introspect on our FPGA simulated designs and try to optimize performance of those simulated systems. So if you recall a little bit earlier, I showed you this simulation of a 32-node rack scale system, right? And so I mentioned that we wrote our own NIC. I mentioned that these systems all boot Linux. So that means we had to write our own Linux driver for our NIC. And then obviously we want to get good performance out of the actual target system here, right? So I said this was a 200 gig network connecting these together, 200 gig network model connecting these things together. So the question is, can we actually drive 200 gigs from within these simulated systems? So the question is, how well does the target system actually perform? So in our original FireSim paper back in 2018, we ran some Baremetal Microbenchmarks, and things looked great, right? So we can tune this benchmark to try to drive a gigabit per second, 10, 40, 100, and it's not shown in this graph, but Baremetal, we can actually drive around 150 gigabits per second. So that's pretty good for these sort of wimpy in-order cores. But if you take a look at another section of this paper where we wanted to run realistic workloads on top, so in this case, we want to run iPerf 3 running on Linux on the simulated systems. Recall that we're trying to drive 200 gigabits per second, but we get terrible performance. What actually ends up happening is that we only drive 1.4 gigabits per second on this network. So for real applications that we care about, clearly there's something wrong, something weird sitting in this big complicated stack that's slowing us down. So if we try to figure out where the bottleneck is, this is actually quite complicated, right? So first off, we wrote our own RTL for a NIC. We wrote our own driver for the NIC. We're running on a Linux port for a relatively new architecture, so there hasn't been a ton of optimization work done. And of course, maybe there's something wrong with the application. That's unlikely, but it's possible. And then these two nodes are communicating with one another through this two-port switch. So this benchmark is basically a client and a server sitting on these two different nodes in this two-node FireSim simulation, and they're just trying to communicate as quickly as possible. They're trying to drive as much bandwidth as possible over the simulated network. So traditionally, if you're trying to debug the performance of this sort of system, well, first you could just guess, right? We tried this, in fact, because it's easy. And you can just Google, how do I make my NIC implementation faster? And you'll get a bunch of suggestions. We tried a bunch of things, but as we'll find out, you sort of need to do things in the right order as dictated by Amdahl's law. Otherwise, you won't see performance improvement. So that was something we tried, not a great option. You can, of course, hire people who know the answer, right? Tons of people have worked on NICs, but as grad students, we can't really do this. So we moved to various sorts of profiling tools. So one is in-band target software profiling. So what I mean by this is software that you run on the system that you're trying to profile. These are tools like Perf or ftrace or strace that just run on the system, sample every so often, and give you some information. The problem with these sorts of tools is that you can't increase the sampling frequency too much because you're adding software to the system. You're running something that takes up its own compute cycles, and so you end up perturbing the results if you try to go for too much fidelity. Another option is to do out-of-band target software profiling. So this is doing things like attaching a debugger to a real chip where you can capture short snippets of a trace port, off of a trace port. So here you can get full instruction traces without perturbing the system, but the problem is that you can't really have enough storage to capture very large traces to do things like performance debugging, usually. So what about the hardware side of things? So there's also tools that let you do in-band hardware profiling. So what I mean by this classic example is performance counters. So we can sample performance counters in the design, but this is also commonly problematic, usually because you only have a limited set of performance counters, and you usually end up having to do things like multiplexing events across performance counters, or if you just want to sample very often and at a fine grain understand what's happening in your system, you'll end up perturbing your results just like the in-band software profiling case. So to address these sorts of issues, FirePerf is going to introduce two new FireSim features. So the first one of these is going to be Tracer 5 with stack unwinding and flame graph generation. And the second one is going to be called AutoCounter. Okay, so what is Tracer 5 first off? So this is a very simple piece of hardware. It's a FireSim bridge. It's a model in FireSim that lets you collect a commit trace from the simulated system and log it to disk. So this can include information like the address of the instruction that's being committed, the bits of the instruction, and various other information. The reason this has to be a model in FireSim is that we want to make sure that if we get backed up on the FPGA, where we're trying to log all of the trace coming out of the simulated system, if we get backed up, we need to back pressure the simulation. So simulated time for the simulated system has to stop advancing when our buffers fill up. So this way we can collect a complete trace from the simulated system without perturbing the simulated system. So stuff running in the simulated system has no idea that this is happening. All that happens is time stops progressing, the design stops advancing cycle by cycle. When these buffers fill up, they get cleared, logged to disk on the host system, and then life goes on. Another nice feature here is the availability of triggers. So we can start and stop this logging on the fly. So obviously we don't want to pay the performance cost of logging these large traces to disk when we're doing stuff that we're not really interested in, like just booting the OS. And so there are a variety of different mechanisms where we can start and stop simulation, both from inside and outside of the simulation. Of course, just looking at this bare instruction trace that you see on the right is not super useful for profiling's sake, right? I don't know about you, but I can't look at this and know where the hotspots are in my code. So we need some sort of visualization. So what we're going to do is do a best effort unwinding of the execution stack that you can sort of infer from the trace coming out of the system. In this case, we're interested in understanding what's happening in the OS. That'll be our primary time consumer on the system. So we're going to correlate the trace coming out of the system with the OS binary, and then we're going to feed it into a tool called flame graph. This is going to let us visualize where time is being spent in our system. And the nice feature here is that we're not really sampling, right? We're just capturing the stack trace every single cycle. And this way we can just collect all the data and just do a complete visualization where we don't have to deal with the effects of sampling. So the second tool I mentioned is AutoCounter. What we're doing here is enabling out-of-band hardware profiling. So basically, we have some signals in our design. They represent events that we want to count. We can annotate those in the design itself, and basically pull out those counter values as often as we want, and we can add as many counters as we want to the system. So the API that we're going to use to do this is called the cover API. So this is an API that's already present in a lot of open source Chisel code bases. This is basically a function that's traditionally used to help some backend learn about an interesting signal. Usually it's some sort of verification backend. This is explicitly annotated by the user to basically mark that a signal is interesting. So in FireSim, the backend that we add for covers in this case is basically treating those covers as interesting events that should be counted. So when the signal goes high, we increment the counter, and when the signal goes low, we decrement the counter, or however you sort of want to count the event. Then we add infrastructure to automatically pull this off the FPGA, and we log it to disk on the host out of band. And it supports that same sort of trigger functionality that I mentioned earlier. So here's an example of annotating the NIC design with these covers. And I'll talk about this in some more detail for the sake of time later in our example. So now we're going to do a case study of actually improving the performance of this system that I showed you earlier using these tools. So again, we're trying to identify the bottleneck in this relatively complicated system. What we're going to do, though, is start a little bit simpler. So first off, we're going to try something called Loopback, which is basically us taking the server and client side of that application and running them through the same machine. So we're trying to decouple hardware and software issues here. And so we're going to use Loopback, which means that we're not involving the Linux driver that we wrote for our NIC, and we're not involving our NIC RTL. So basically what we're trying to figure out here is, okay, this is a new architecture with a new Linux port. Let's just see how fast this Linux port on this particular microarchitecture can handle packets. Now you might ask, well, okay, we're just measuring software here, so what about software profiling? So we try this out. We can try a sort of simple profiling tool like strace. Let's just see the sequence of system calls that the system is making. So maybe the application is doing a bad job batching out its reads and writes to sockets, and that's why we're getting poor performance. So you might ask the question, well, what's the overhead of doing this tracing? And so this example will answer that question. So first off, we can ignore strace and get a baseline number for that system I showed you on the previous slide, where we're running iPerf 3, the client and the server running on the same system, talking through a socket that's configured for Loopback, and we can drive 4.8 gigabits per second. So again, this is not involving a NIC, not involving a real network. Now, something very confusing happens when we run this in strace on this system. Our performance actually increases when we run inside strace. And I'll tell you why once we sort of figure out where our performance bugs are in the system. But this is a very confusing result. We run inside of our software profiler, and it has totally changed the behavior of our system. So what we're going to do instead is collect flame graphs with Tracer5 and FireSim. So here's the flame graph of that baseline loopback number, that 4.8 gigabits per second. So what these flame graphs essentially show is total benchmark cycles on the x-axis. So that's time spent, not ordered time. So you're not seeing time progress on the x-axis here. This is just basically a histogram. So the stacks that you see here are actually stack traces. They're actually call stacks in the system. And basically, if you see a bar at the top of one of these stacks that is very wide, that is some routine in your system that's taking up a lot of time. So something right off the bat that we see is problematic is this ASM copy to user and copy from user assembly sequence. So I'm just going to refer to this for the sake of speed as copy user from here on out. So what is copy user? So this is a memory copy between user space and kernel space and vice versa in the Linux kernel. So this is an assembly sequence that's written per architecture in Linux. And as it turns out, in the RISC-V port, there's a performance pathology. And that is that when your source and destination buffers aren't aligned, the implementation resorts to a byte-by-byte copy. So obviously, if we do this, we're making terrible utilization of our memory bandwidth. And the funny thing here is that, of course, this is only triggered when you get non-aligned buffers. So when you happen to be allocated non-aligned buffers, you see bad performance. So what's actually happening in that strace case, I don't have an explanation for why, but when you run inside strace, you get aligned buffers more often. And we actually confirm this just by hand instrumenting the kernel to print out the addresses And for some reason, when we run inside strace, we just get aligned buffers more often. Obviously, this sequence can be optimized, so we did so that we can actually do word-oriented copies for wherever we have 8-byte aligned portions. And so we added some code here that's in the process of being upstreamed to the Linux kernel for fixing this problem just purely in software. So if you do this in the loopback case, we now go from 4.8 gigabits per second to 6.3 gigabits per second. A nice thing here is that because this is just a software fix, we can actually immediately deploy this on real RISC-V silicon. So the Hi-5 Unleashed is, again, a quad-core in-order RISC-V system, and it happens to have a 1 gigabit Ethernet NIC attached to it. So what we did here is we took that system literally over an Ethernet cable, attached it to another system with a 1 gig NIC, and we measure performance running iPerf3 client on one side, the server on the other side. So same benchmark we've been using all along. If you look at the baseline copy user and compare it to our optimized copy user, we see some pretty large speedups just by making this software change that we discovered with our tool. And in this particular highlighted example, you can actually saturate your 1 gigabit NIC in more cases. So I don't have time to show you in this talk, but in the paper that we presented at ASPLOS, we do some AutoCounter-based analysis where we stick some performance counters inside the core to show that this software, this improved software version of copy user is basically as optimized as you can get for this particular microarchitecture that we're modeling. So obviously, if we want to get better performance, we probably want to hardware accelerate this thing. So we have Huacha, which is a vector accelerator. This is an open source vector accelerator that you can plug into your Rocket chip-based system, has things like virtual memory and Linux support. So what we'll do is plug in Huacha to our simulated system and have the kernel dispatch these copies to Huacha to get high memory bandwidth utilization. So once we do this, we go from our 6.3 gigabits per second software optimized case to the 16 gigabit per second number you see here. So this is still in loopback mode. Now, if we switch over to the actual networked case, so now we're actually simulating 2 nodes, talking through our NIC implementation and the simulated network, we see an improvement from 2.1 gigabits per second to 3.2 gigabits per second. So you might ask why the baseline here is 2.1 gigabits per second as opposed to 1.4, which is what I showed you earlier. That's just an artifact of the fact that software has evolved since we wrote our ISCA paper back in 2018. Okay, so let's look at the networked flame graph now. So this is no longer the loopback case, but we're looking at the networked case with our copy user optimizations so far. So now you'll notice that all those calls to copy user have sort of disappeared here. They're relatively narrow bars, but we see this do checksum sequence now showing up, taking up a lot of time. So if you're familiar with NICs, you might say, yes, this is an obvious addition that you would make to any modern NIC, and that is true. This is actually one of the features that we tried just randomly adding at the beginning before we had these profiling tools. But the problem, of course, is that if you don't fix that copy user bug where copy user was dominating your runtime, adding this checksum offloading feature doesn't really make a difference. And if you're trying to analyze the trade-off of adding this complexity to your RTL versus maintaining it, and the actual performance improvement you get, it doesn't make sense to have that unless you see a real improvement. But now, once we've addressed that copy user problem, and then we add checksum offloading, we actually see a significant improvement. So we go from 3.2 gigabits per second to 4.2 gigabits per second on the system. Okay, so at this point, if we had looked at another flame graph, we wouldn't really see any real hot spots showing up. So what we're going to do instead now is context switch and look at what's happening inside the hardware in the system. So what we're going to do is look at the send request queue inside the NIC that's doing the sending. Because, of course, if we aren't sending at a particular rate, then the receiver has no chance of achieving a higher rate. So what this is showing you is how occupied the queue is inside the NIC, where the OS comes and writes a descriptor that tells the NIC to go fetch a packet from somewhere and send it out. So ideally, what we'd like to see here is high occupancy, at least for some cycles, because that basically means that the OS is coming along, writing in a nice big batch of packets to send, and then going to do other work. What we don't want is to come write a single entry, go do other work, the NIC quickly sends that out and then has nothing to do. So if we look at our baseline case where we started, we're actually doing pretty terribly. we only ever see an occupancy of at most 1. We've hidden the 0 bar here so that the graph looks good. But we're obviously going to get terrible performance in this case. This dark gray bar that you see in the middle is with the optimizations that we've implemented so far. So we've improved a little bit. We still don't see any occupancy greater than 1. So this motivated us to say, well, okay, where is Linux actually writing into this hardware queue? It's a sequence called IceNet start XMIT. This is where we're directly doing MMIO reads and writes to the NIC queues. What we want, again, is to be sending packets in bursts. So now, because we're actually taking the full trace out of the system and not just sampling the stack at various points in time, we can actually look at the complete trace and notice that the completion interrupt is actually happening immediately when this IceNet start XMIT function re-enables interrupt. So this means that we're literally writing a single frame and then taking an interrupt and going to do a bunch of other interrupt handling stuff. This is actually pretty difficult to observe with perf because perf sampling itself relies on timer interrupts. You can add some like NMI functionality to try to make up for this, but RISC-V doesn't have this functionality yet in the Linux port. So anyway, motivated by this, we modified our NIC driver to support Linux's NAPI, which lets you have interrupt mitigation. So basically, we adaptively disable device IRQs and switch to polling when we're under high load. So this amortizes that interrupt cost and actually lets us write batches of packets into this queue. So now if we zoom back out in this graph, we have these light gray bars once we've implemented this optimization, and we're getting much better queue occupancy in the system. Once we do this, our network performance increases to 6.7 gigabits per second. Okay, so what's left here? So if we looked at another flame graph, we wouldn't see any bottleneck functions. Our hardware queue utilization has gotten better, but NIC resources are still sort of underutilized because of software processing overhead. Of course, this is a relatively wimpy system, so at some point, we're just going to exceed the capacity of the system to drive the network. One last thing we can do, though, is amortize software processing overhead using larger packets. So we're going to switch to using jumbo frames. What we're basically doing here is saying that the Ethernet payload size is larger than what we had before. So this is commonly used in data center contexts to basically amortize the overhead of having headers. So once we do this in our dual core network case, we can hit 17.5 gigabits per second. Of course, you might say, well, okay, that was sort of a random optimization. Why did you try this at this point? And the reason we did this as the last step is, again, this is one of those optimizations we tried early on, right? We knew that jumbo frames are used commonly to get higher bandwidth, higher good put in your in data center networks. But if you actually implement this optimization without fixing all the other problems we've seen so far, you don't get speed up. And again, you're just adding implementation complexity for no speed up, and so then the trade-off doesn't make sense. So this is basically just a summary of the different optimizations we've made so far. So we can hit 17.5 gigabits per second now on the system. And so if we compare this to a host on EC2 that has 100 gig networking, various sorts of offload, that sort of stuff, if you again run iPerf 3 on 2 nodes on EC2, you'll hit sort of the same order of magnitude of performance running a single connection between these two. So in sort of the single core, single connection case, we're getting competing or competitive bandwidth with this sort of system. Of course, on these real systems, if you now run many connections across many cores, you'll actually be able to saturate the network. We're not quite there yet, and that sort of multi-core scalability is something we're still working on. Okay, so I'm going to wrap up just by talking a little bit about the FireSim community. So there are a couple of companies that have publicly announced that they're using FireSim. We've recently integrated into Chipyard, which is that large framework I told you earlier that lets you compose RISC-V SoCs. There are a bunch of projects now with public FireSim support, and I talked about a lot of these earlier. They've been some early academic users back in 2018, and the list is constantly updating, and you can check it out on the website. We're also sort of pushing into education now. So at Berkeley, in our upper div computer architecture class, as well as our grad computer architecture class, we teach FireSim through labs. We've also run some tutorials. We had our first full day tutorial at Micro 2019, where we actually gave people access to EC2 instances and have them really use FireSim, and we had great feedback from that. We're also planning to do this at ASPLOS. Obviously, we couldn't due to the cancellation. And we have a growing community around FireSim, and we welcome you to join. Just to talk about some new features. So FireSim is obviously being actively developed. We shipped our 1.9 release back in March. This open sourced a bunch of those FirePerf features in time for ASPLOS. Our next release, 1.10, is going to contain a bunch of the things that I told you about. One thing I didn't tell you about that's commonly requested is that we now have support for multiple clock domains. So this is staged on the dev branch, sort of our developer branch of FireSim. That Fromajo support is a PR that's currently undergoing review. And we're also working on adding support for local FPGAs. And this is actively being worked on too. Okay, so to wrap up, FireSim is basically a tool that lets you do productive open source FPGA simulation. So here's where you can find the source code. What we've essentially built here is an easy button for doing these fast FPGA accelerated simulations. You can bring your own RTL. We've done a ton of work to automate the process of running these simulations. It's all hidden behind this FireSim command line program, where we've essentially tried to design it like if you've used Docker or Vagrant, but this is for FPGA simulations instead of containers or VMs. A nice thing here is for reproducibility. Scripts can call lists to completely automate the process of running FPGA simulations. So for example, all of the graphs in our ISCA 2018 paper, you can reproduce those things end to end by running this one script. So this literally starts from building FireSim, building the images, building the software stacks, deploying onto FPGAs, running all the simulations, collecting the results, and even running the Python scripts to generate graphs. And we have things for something that you might actually want to run, for example, collecting all of the spec 2017 reference input results in a day. There's tons of documentation. We really tried to make this accessible and easy to use, so you don't have to know all of the internals of FireSim, just use it to model an RTL design. And in particular, if you're in academia, AWS provides grants for researchers to use EC2, including F1. All right, so with that, I'll wrap up, and I'm happy to take any questions, and thanks for watching this talk.
Thank you for a great talk, Sagar.
Yeah, great talk.
Thanks.
So I was able to clear most of the questions. So I cannot test it because I cannot post questions, but the people in the audience can post, and then we can give time. But for they are doing so, I have some questions for me while they're trying to think what to ask. One thing I saw that you are doing the Fromajo,
yeah,
which is the student. We have a student working on Fromajo. He was on Esperanto,
yeah,
working part of the flow here, but he was not able to connect here today. So the current version that is being pushed out, there is no multi-core. So it only does traces code simulation for single core.
Yeah, that's right.
That's what you are doing too, no? So you are able to check the trace for one core.
Yeah, exactly.
Okay, now it's because we are working on the extending for multi-core, but from an FPGA point of view, it might be tricky. It will require more trace information.
Yeah, we would be happy to talk about. I can connect you guys with the student here who's working on integrating Fromajo with FireSim.
Okay. Now, one thing that we are trying to work here is try to improve the productivity of the tools. Not so much like trying to do a FireSim. It's more like try to make people who develop FireSim to be more productive. So I have some questions that I'm curious. The compilation time, imagine that you submit to on the grid and you populate the boom with 6 cores that you're saying that it fits. How much time does it take to compile, more or less?
So
and I'm saying one instance you just want to run GCC on a spec.
So if you're like maxing out the system, so you're basically trying to fit 6 boom cores with our resource optimization, so you can actually fit them on one of these FPGAs. That's I think around like that'll take about 4 hours. That's sort of end to end. That's including the chisel elaboration, the shipping out to Vivado, running Vivado, getting a bit stream at the end.
Okay, but most of the time, if it's taking so long, it should be on the place on route on the Vivado side, no?
Yeah, I'm pretty sure that's the case.
Because it's congested.
Yeah.
Now, just curious, from a FireSim developer point of view, if you were having 2 wish lists on the tools to be better or different, what would you have? So it's a wish list, so it can be, as long as it's not magic, or it can be magic if you want, but.
Yeah, I mean, obviously, much faster FPGA flow. So like the Vivado build process, there's commonly just this problem of like, you can get pretty far in a software RTL simulator, and because FPGA builds take so long, you know, trying to figure out, well, should I build an FPGA image versus just trying to debug this by hand in a software RTL simulator? So we don't do anything to try to make FPGA builds faster. So much faster FPGA builds would help us a lot. I think that would probably be the #1 thing. I think the second step would probably be, you know, if we could use our own debugging tools on the simulator when we try to debug bugs in the simulator. That sort of like nested simulation is not possible yet. So maybe something like bringing some of these features that do make sense to sort of the FPGA prototyping level, where, you know, you can have ILA type things, but apply some post-processing or something there to get more useful information out of them.
Because can you dump a checkpoint state and then load it with BCD, BCS or something like that and debug to have full trace debug? Or do you just, or can dump a BCD full, can you dump like an equivalent of a BCD so you have full visibility?
So you can't yet. So there was some earlier work from Berkeley called Strober that did that. The problem with this is basically mapping what's running on the FPGA back to the software RTL simulator. So obviously, if you're just doing like architectural state, that would be not so bad. But if you're trying to get like all of the microarchitectural state and all of that stuff, I think the difficulty there in making like a real generic solution for that is mapping it into what's in the software RTL simulator. So that's why that feature basically doesn't exist. So when Dongyu did that back in the day, it was sort of specialized for the particular system that he was modeling.
Okay, so then to estimate power, that's what it was used in the Strober, so it will be, so you don't have the same.
Yeah, so that's basically why we don't have that feature right now. It's just because doing the mapping generically is somewhat difficult.
So then on the trace bit, you have to instrument before what is the thing that you want to trace, and it will be just dumping the trace out.
Yeah.
But you have to mark it. How do you mark it? In Chisel, or how do you mark those things?
So for Tracer 5, we're just expecting the system to have a trace port at the top. So like Rocketship and Boom implement the same sort of trace port that's exposing just a bunch of signals. When you like tape out the chip, that can get attached to like a debugger or something like that. The sort of more generic version of that feature is the printf synthesis. So there you can go and write a printf in your Chisel RTL. And then obviously when you change that, that has to go through the whole build flow, FPGA build flow and stuff like that. So there's no like ability to do that dynamically yet.
Okay.
I have a couple questions, but I want to give a chance for anybody in the audience that has questions too. Please either type them in or raise your hand. If we recognize you, we'll definitely invite you to use your microphone. While they're perhaps typing up questions, the one question I had was, how are these larger designs split across FPGAs? Is that manual, or is that to be at network links, or?
Yeah, so that's basically manual. So whenever, so right now we assume that a design does not need to be split across FPGAs. So the way we try to make those designs fit is by making better utilization of the resources that are there. So that's like that Boom example. The partitioning in those like big network simulations is manual. So we manually express like in Python a topology, which is a bunch of nodes connected together by some links and switches. And the FireSim manager will basically map that down to the host system. So you have to have, in this case, you have to have basically an Ethernet network exposed at the top of your system to get that sort of distributed simulation.
Great. My other questions are kind of about some of your experiences with various tools. You mentioned for inputs, you guys are considering, PicoRV through Yosys, or even accelerators from, I guess, Vivado HLS. What's the experience of getting those things into Fertile?
So I'm not sure if I mentioned this, but the Vivado HLS case and the NVDLA case, we're actually ingesting those as black boxes. So what that basically means is that we literally stick in like a clock gate at the top of the top level of that chunk of IP. And that's how we get the ability to control how it advances. So those designs are not getting converted to Fertile. They just get plugged in as black boxes. And so they can plug into the simulation and you can get like the correct performance measurements out of that, but you can't do most of these other nice features that I've talked about, because those require actually doing Fertile transformations. The Pico RV32 case was a simple test design that we wanted to push through the actual Yosis flow to get Fertile. That's still sort of hacky right now. So I think there's a branch on FireSim, but it's not mainlined yet. There are some things that I think need to be cleaned up a little bit in the Yosis to Yosis Verilog to Fertile flow. I think one of those things, for example, is detecting combinational loops. So I think there's sort of a discrepancy between Fertile and what Yosis expects, or what is there in Verilog, with how you sort of index into things and what happens when you connect together, pieces of a field. So sometimes we get like incorrect identifications of combinational loops. I think that was probably the main issue that we encountered doing that work.
Great. I'm going to pause for a second for any more questions from the audience. And I guess we should thank our speakers. Thanks again for a wonderful talk, Sagar.
Thanks for having me.
Yeah, thank you. Very safe. A lot of work. I'm sure there is someone more than you, otherwise we're super productive.
Yeah, no, it's a big group of people from the front page of the talk. Yeah.
Okay, and next week we'll have Sheng Hong talking about, I believe, LNAS, right?
Yes, it was going to be LNAS and live LGraph, and a little the Fertile Verilog interface. Maybe he talks about that.
Well, great. Okay, well, thanks, folks.
Thank you.
Okay. Thank you. Bye.